Transformational Creativity in Science and Graphical Theory. Also with Professor Varshney. So, uh, so do y'all want to introduce these concepts? Uh, because I know you've worked with them probably more than I do. So if you want to introduce them, you can, or if you want me to introduce them, it's up to you guys.
Yeah, I mean, we can.
Okay.
Sam, do you want to, or I know you've read this.
Yeah, sure.
Yeah.
So, yeah, Thomas Kuhn wrote this great book, The Structure of Scientific Revolutions, which has been really influential towards modern philosophy of science. And he, uh, I think one thing I'll say here is, although I explicitly delineate these three phases, he doesn't actually enumerate them. He doesn't say phase one, phase two, phase three. That's sort of how I summarize it. But yeah, normal science, the first phase is based off of really just extending an existing scientific paradigm. So someone will establish a system, say Newtonian physics, Newtonian mechanics with the three laws, and then all the subsequent work will be based off of those foundational principles. But at some point, some brilliant scientists might realize that, well, this system doesn't actually explain everything we want it to explain, or maybe anomalies and inconsistencies will emerge from that paradigm. And that's when you enter phase two, the recognition of anomaly, which will cause this phase of extraordinary science. And this is typically characterized by a recourse to first principles, a recourse to philosophy. And ultimately, what happens is the first principles are rethought, and a new scientific paradigm emerges that reconciles the inconsistencies and anomalies that were recognized with the previous one. And that's where you get the scientific revolution. And it can be really disruptive as a scientist when this happens because, well, as we show in the paper, the foundational principles change. And this has a cascading effect on everything that depends on those foundational principles upstream. Any questions about that?
Awesome. That's a good description. Yeah, I've been reading this scientific structure of scientific revolutions a bit myself. So
Yeah, it's a really good book.
yeah, I think
It's
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 really
definitely,
compelling.
yeah. Yeah, if you want some recommendations for things to read after that, mostly mostly works in philosophy of science that were subsequent. I have a long list of things that are worth reading. I would say most specifically Conceptual Revolutions by Paul Thagard, I think really makes a big step. It's not just a philosophy of science text, but it also introduces a lot of useful mathematical constructs that I think are poised to play a role in some of our future work.
Yeah, maybe also worth. I think Sam, you sent me this once. The guard outlines a structure that's very, very similar to the one that we introduce in this
Yeah.
paper.
So,
Uh,
it, yeah, Thagard. I actually read his book after we finished this entire project, so I wasn't able to retroactively go back and add the citation and say what we
beating
have is fairly similar.
plagiarism allegations.
Well, it's funny because I sent him the paper and then I said, I haven't read your book, but I'm reading it next. Looking forward to it. And then I started reading the book and I realized, oh well, it's very similar. But it's actually when you get down to the details and having had some time pass since I read his book and letting it digest and absorb, I actually realized that ours is quite distinct from his. His thesis is that scientific change and revolution stems from disruption in part kind hierarchies, as in X is a part of Y or Z is a part of A. And if you read the book, most of the examples he gives are for natural science and chemistry, things like that, where it's very common to discuss this is a part of that, or uh, in biology, those taxonomy trees where mammal is a part of XYZ, etc. So I think
Kind of
his
like a different
theories,
layer of abstraction or like a Like
Yeah.
I've been thinking about this kind of layer abstraction idea where kind of a neuron will, like, the inputs to a neuron are like a different layer of abstraction than the neuron that is connected to them, and then if that makes sense. Like, I mean, I've been thinking about that from like a neural network perspective, like the to represent a layer of abstraction. It's kind of like going. I mean, neurons are typically organized in layers, so I mean, I guess that it just makes me think. I think that that's like a way that the neurons kind of abstract is just through their connections and um, the connection, because neurons only get, they're like they have a bunch of inputs but only have one output. So it's, I mean, typically only have one output, not in a neural network, not in an artificial neural network, but in a biological neural network. But I think that's,
Oh, you're speaking about biological networks,
yeah, because I mean,
not.
well, yeah, I
Okay.
mean, in biological neural networks, you only have, like, you have the dendrites and in the axon, right? So it's
Yeah.
like the but the dendrites, there can be like 10,000 of them or something, whereas the axon, there's usually one of them, right? So it like
Mm.
and then the cortex is organized in these layers typically. So it's like that's, but I think that certain people only operate, like, different people operate at different layers of abstraction in some way, and it's and that's kind of, I don't know, it just made me think of that with the hierarchical organization of different, of how, and like X is a part of Y or whatever, is like that kind of made me think of that. But
I think yeah, you interpret it in a more theoretical sense, which I agree with. But Thagard meant it in a more physical sense, like wood is a part of a table or a leg is a part of a chair. He meant it very
that is like a
fine.
layer abstraction though, because like
Yeah, I
you
guess you
look
could
at a
say that.
table and you say, okay, well, I could, well, like, you look at a leg and you look at two legs and you look at four legs, and then you look at the um the top of it, it's flat, connected to these, and then suddenly the neuron fires. It's like, oh, that's a table, you know. I don't
Yeah,
know.
sure. You can make the claim that it's objectification, distinguishing objects and perception. In which case, sure, it's a form of abstraction.
Yeah, yeah. I was just that's. I mean, I don't think we're disagreeing.
Yeah, yeah, no, I agree.
Okay.
But yeah, I would suggest the guard's book. It's pretty good. And
Okay.
then uh, he has a later book, I think, from the early 2000s, Computational Philosophy of Science, which is not as good as his earlier one, Conceptual Revolutions, but it's also possibly worth a read at some point.
Okay. Um,
So we get to Bowden.
Conceptual resolutions. Okay. Yeah. So, all right. So yeah, what did? So I guess I was wondering, like, how do the two relate? I mean, I guess we could introduce Bowden first too. So.
Oh, yeah, yeah. Well, the thing is, when you write a paper, you do it and you explain how the idea or discovery should have happened. But this was not actually how we thought about any of this. Like the idea that we conceived was certainly heavily dependent on Bowden's three categories, and probably at an unconscious level, reading Kuhn's book influenced it. But we arrived at the theory more so by just a critical examination of really impactful works in science and philosophy, like Nietzsche's Genealogy of Morals, Girard's Mimetic Theory, Kant's Critique of Pure Reason, and sort of recognizing patterns. And then obviously some of the examples we give in the paper, like the revolution from geocentrism to heliocentrism, non-Euclidean geometry, the discovery of that, and then Einstein's theory of relativity. So the way we actually came up with this paper, the core contribution was by recognizing these patterns that were persistent across all these breakthrough discoveries. And then to really substantiate the claims, we contextualized it within Kuhn's model, but we weren't initially actively thinking of Kuhn's model. We just sort of, when you write the paper, you present it how it ideally should have been discovered. So I guess that's one idiosyncrasy with science and peer review and writing papers is, yeah, it often doesn't really explain how the discovery was made. But in any case, we can get to Bowden's three types of creativity, which I will say I think this distinction is not as well defined anymore. But maybe we can get to that later. So
It's useful
she,
for thinking about, I think.
I think it's useful initially, but I think it's due for a revision. Maybe this is something we work on for next year's
Yeah.
ICCC. But anyways, she delineates three forms of creativity. One is combinatorial, and this is based heavily on some work in philosophy of mathematics in the 20th, 19th century. I think the French mathematician Poincaré, he has some popular quotes about this that get referenced all the time. And then also Arthur Koestler's The Act of Creation, his 1964 book, where he talks about biassociation of matrices of thought. So the idea here is when you come up with a new idea, it consists of a combination of existing components that you already knew, that were already in your background knowledge. So in this sense, nothing is truly novel. Everything is just a combination of existing components.
So you can kind of think of just computing out, like you could compute out from um some set of kind of, well, I
Yeah,
guess.
yeah. Or even just think of going back to philosophy of mind, epistemology, metaphysics categories, right? Starting with Aristotle, going all the way to Kant, critique of pure reason, categories of the understanding. You can argue that everything that you can possibly do is just a composition of those categories applying to your sensory experience. So I find that, yeah, thought tends to be compositional. And this is sort of corroborated by the structure of neural networks and transformers as well. So this is another recurrent theme in science of intelligence, that really a lot of powerful things can be built from these compositional systems. They just repeatedly apply compositions to get more and more abstract representations. And eventually you have sort of mind-like properties that emerge, as you were alluding to earlier.
Yeah. So then I guess, so we have these like exploratory creativity, transformation creativity as well. So I mean, the I think, yeah, I mean, it makes sense that later in the, as we get more to the graphical theory, these will become more formal and rather than just kind of references, but they're useful to
Yeah.
think about because,
Yeah. And then briefly, the exploratory transformational distinction. This is visualized pretty nicely because exploratory really corresponds to normal science. It's when you have existing rules and constraints, and to do something new, you're simply following those rules.
Mhm.
Whereas transformational creativity is what happens between phase two and phase three, where you modify the rules of the game, the structure and constraints of the scientific paradigm, and that leads to an entirely new space.
okay, yeah. So, um, I think, and we're also gonna go more into exactly how the that or not. I mean, yeah, I mean how exactly that happens in the graphical theory. So, um, does anyone have any questions before we move on? Okay, so let's move on. So, uh, we can. So I guess, um, before we get too abstract, I think what I understand from the graphical theory is that there are edges really representing the how different how different nodes depend on each other in terms of it. But correct me at any point. But
Yeah.
it seems like it's
I mean,
the edges are representing the constraints on the system.
I
Uh,
think that's probably like a more accurate characterization, just because in the in the language itself, or in the language of the conceptual space, a dependency is characterized as um, some subset L prime of L, which is the larger language. So when you traverse up the graph, so back towards the axiom nodes, you expand you expand on your initial subset L prime, and keep adding and adding and adding more upstream rules. So in this sense, you said it was more of a constraint, correct?
or I'm just kind of thinking about what it
No, I
I
was gonna say I think that's a good way to think about it, because the constraint has it's an easier way to conceive of in English what's happening in the graph than the dependency model.
so so I guess just to make it like
Yeah. So
as simple as
um,
possible, just to start out with maybe how so what does like an edge represent? What does a node represent?
Yeah.
so
So
a node is a set, right? A node is a set of possible artifacts that can be created. And then if you look at bullet point 2 on the right, if you say I have an edge from U to V, then I'm saying that U depends on V. So when you consider V, which is a set, and you look at U, which is also a set, U is a subset of V. So it, we have the equality underneath, but think of it more in terms of just it's a proper subset. So when you say there's an edge between U and V, those two sets, you're saying um, U has fewer elements. You're restricting the space of possible artifacts that can be created. That's what the edge is saying.
another way to think of it in a derivational sense is you have a, a theorem or a set of theorems from which um, another theorem can be derived, but that theorem itself doesn't contain as much derivational potential as the set from which it was derived. Um,
Okay. Okay, so
Yeah, think of
you
it
can derive
deductively. Like the
okay, yeah, that makes sense.
yeah. So you actually, I mean, math is the exact instantiation of this entire framework. You have these very general statements that are made, axioms, and then from there you deduce more specific properties, and the truthity or falsity of the statement is guaranteed by the axiom. So if the axiom's true, everything else is true because you're going from more specific to
So
uh,
an incoming edge is that it means that that is a so just and that is an sorry, if it has only incoming edges, then it's a axiom.
yeah.
correct.
Um so if there's a path going to a node, then that means that it depends on on the second node, the one that it's going to, right?
Right. Yeah. Bullet point 2 on the right gives the total, um, like just the first few mathematical expressions there.
Yeah.
The tuple U comma V is in the edge set if and only if U is a subset of V. So U has to depend on V.
The other point I'd make here, I actually think that we call L subset of E, where E represents a class of recursively enumerable sets, I think it's actually should be recursively axiomatizable sets to be more precise, because we define, well, any conceptual space necessarily has some set of axioms which can be decided, like the belonging to the space can be decided by a Turing machine. Recursively enumerable sets don't presuppose any such set of axioms.
Yeah.
So, minor pedantic point, but kind of interesting.
It doesn't impact any of the
Yeah, I
the
know.
practical implications here. But if someone was to extend this work in a more theoretical direction, then
Yeah,
which I don't think is really that important right now. But
yeah.
then it would have to be more specific
I mean,
about.
all recursively axiomatizable sets are also recursively enumerable, but vice versa is not true.
Mm,
Okay, so should we move on to the next?
sure, yeah.
Okay, so I guess um, so now we see the graphical application to scientific theories. So the there are some graph operations that one can do, um, and just I guess I guess so just bring it back to the earlier point about creativity. So what is what in terms of the operations would kind of correspond to a Bowden like process or like a
Of exploration or
or like an
transformation.
exploration transformation or um combinatorial
Yeah,
or
so
any of them.
one of the things on the earlier page, which isn't pictured here, is the vertex and edge modifications. So given a graph, the most transformative thing you can do, like as was done with the discovery of non-Euclidean geometry, or what we're saying with from geocentrism to heliocentrism, is to take an axiom and then modify the axiom via what basically what's not pictured here is the graph edit grammar, which is it can either consist of edge modifications, so adding or removing an edge, or it could consist of vertex modifications where you could add or remove a vertex, or you could change the compositional content of the vertex, which is just pretty much the same thing as adding a new one and replacing it by removing the old one, putting it in that
So
spot.
what would it look like if you like say you want to remove an or you want to like add or sorry you want to modify a axiom?
Yeah.
What would have to occur for that to be enough for that to maintain for that to stay valid in a new system after
Oh, it just
modifying
has to
that
be a
axiom?
directed Yeah, the only constraint is it has to be a directed acyclic graph.
Mhm.
So what would
So
so it would just have to um but so say like we were going from the geocentric conceptual space S to the heliocentric conceptual space S prime,
yeah,
then like so you have these planetary predictions and you have a new axiom, Earth
yeah. The
rotation.
interesting thing
Or no, wait, no,
is
it's
the
not a new
interesting
axiom. Sorry, it's
thing.
not a new axiom. Sorry, they have you have a new kind of rule, right? Um, Earth rotation.
No. So you want to start from the bottom. Yes, start from the bottom up.
Okay.
Always start with the axioms. So you imagine you have a proposition as you would before heliocentrism became popular. And the proposition would say, well, the Earth is at the center of the universe. Oh, that's axiom A1. And then axiom A2 would be, and everything revolves around the Earth according to uniform circular motion. So
Okay.
you have these two propositions which are just treated as axioms in this sense. They could be generalizations and conclusions from empirical sense data, but for all intents and purposes here, we treat them as axioms. And then what happens is you would make the realization that actually the Earth is not at the center. So you would logically negate the axiom, right? The original proposition states the Earth is at the center of the universe, and then you would take not of that proposition, and then you would realize actually the new proposition should say the sun is at the center of the universe, or to be more precise, the solar system now. And then you would also discover that the motion of planets is not uniform and circular, but it's actually elliptical. And then from there, the entire conceptual structure above those axioms now has to change to reflect the modifications made to the axioms. And you get this emergent rule, which is the Earth's rotation, the 24-hour day.
And
It's a very crude toy example here, but the key thing to focus on is it's the modification to the axioms that leads to these upstream effects and modifications, and we term that transformation.
the other sort of interesting thing to note here, to Sam's earlier point about the three categories of creativity perhaps not being the best examples, say instead of negating an axiom, you introduce a conjunction. So you say the Earth is, everything revolves around the Earth, and the Earth is a third planet from the sun. In some sense, you do transform the axiom, but the result resembles exploratory or exploration a lot more than it resembles transformation. Um, and so you have some sort of like uh, edge cases here, which may fit both exploratory and transformative criteria, which suggests that perhaps those aren't the best way to delineate.
Yeah, the key problem with Bowden's distinction is it's she has these three categories, and I don't remember from her book if she makes the explicit claim that they are distinct, that there's no overlap between them. I don't think she even addresses that. But it's clear now that this is probably not the best way to be looking at the problem. So given our mathematical formalism, you could say it's transformation if something is modified. But then you could also go one step further and quantify the degree of transformativeness.
Yeah.
And then
So I have a
really
question. I have another question though.
exploration.
Like, what can you
Yeah.
preserve about the? So you have some original constructed graph of implication. Um,
Mm.
how could you preserve, like, like if you modify an axiom, like, how do you know what needs to be changed and what doesn't? Does everything that is, um, say, has that axiom that relies on that axiom, does everything that has to be changed, right?
Right. Yeah. So
So is
the
there anything
dependency
is there
structure.
anything you can preserve within the dependency structure, or is also kind of um that also depends on
The- the-
that axiom,
the-
or
the- Theoretically, if you modify an axiom and there is a path from any node to that axiom, then something about that node has to change. So it's going to ripple upstream. The only nodes that wouldn't be affected are ones that don't have a path to the modified axiom.
and then I guess I'm wondering if you could, is it possible to like, so this we have these like four nodes. It's a kind of a toy example, but is there like, could someone represent this on a finer graphical scale? Like
With more nodes,
more nodes and like
more
more
detailed.
axiom, a lot more. Like, would that? Do you think that would modify how? Like, would it help to just create a lot more detail and like a lot more nodes and a lot more edges? But like,
Oh yeah,
how does
for
increasing
sure.
the
Yeah.
graphical fidelity or help with the help with like understanding how
Uh,
the axioms relate and the resulting downstream theories?
I think doing more illustrative examples will, I think it will be helpful for really every aspect of the paper. So anything you can think of, any question you might have regarding what would the graph structure look like, how does transformation occur, more in-depth examples will provide some insight into all those possible questions. And they really should be done as part of the future work.
Another interesting follow on, Evan, to your earlier point about whether or not axiom modifications can preserve upstream rules is if you take two like previously disjoint conceptual spaces and find some unifying axiom that on which both of their respective axiom sets depend, you might be able to preserve the integrity of the graph while also introducing some new governing set of axioms that previously wasn't discovered or part of the graph. Although that would probably be more of an exploratory instance than a transformational instance.
Interesting. Okay. Any questions on or discussion points about this slide, this part? Okay, I guess then we can move on to the next, which is what I find pretty interesting, is that you could use this in um, this graphical model or this graphical theory in uh, for AI Metascience. And why don't y'all talk a little bit about how this works and how would each of these steps occur? Like what would be a kind of a system that might be able to um, go through these steps?
Yeah, so we're actually building this out. That's one of the papers we want to get into ICLR this year.
The
And
system is having a
obviously,
valid API key.
What was
yeah,
that?
so obviously
That was a joke.
Oh,
Sorry.
okay.
obviously the main starting point here is data. So for the most part, you're just going to be looking at academic works data. So it could be survey papers. In AI, it's popular for most of the work to be disseminated through conference proceedings. But then in other areas of science, journal papers like in Nature or Cell are more common. So just imagine you have a huge collection of data representing background knowledge about a particular domain. Then what you would want to do is construct the scientific conceptual space for that field. Now, if you do it for the entire field of, say, chemistry or computer science, the graph is going to be intractable to construct. It's going to be too large. What we actually suggest is starting with a small subset of a field. So maybe just looking at a specific area in AI or a specific area in chemistry. I can't speak to other disciplines since I'm not as familiar with them. But for example, it could be a very niche subfield in AI, such as
Yeah.
sparse autoencoders for LLM mechanistic interpretability. And then you would collect all of the relevant papers about that topic, and you would construct the graph representing the dependency structure between the rules and the axioms. Now, that sounds easy. We've laid out what the graph should look like mathematically with clear precision, but doing that, actually going from data to graph, it's very difficult because you can't leverage existing knowledge graph techniques here, since we've essentially postulated a more causal deductive structure, whereas knowledge graphs function much like what I referenced from Paul Thagard, those part-kind relationships. So knowledge graphs have entities and relationships between them, um, but we're specifying something with a lot more causal and deductive precision, but
Yeah.
something which we claim actually underlies most of how scientists approach problems in their field or subfield. So it's these small deductive pockets, and maybe that they're not even small if it's an area like logic or math or the more pure theoretical sciences, but it's these deductive graphs that scientists are constantly having to work around and obey in order to explore within their conceptual space. But in any case, that's the abstract formalism. Then third, this is something that I wouldn't say is 100% necessary, the problem identification, but it's something I just included to stay consistent with Kuhn. Is, as we talked about, what often leads to the revolution is this period of a recognition of anomaly and crisis, and then it'll prompt extraordinary science to occur. So I was thinking it would be appropriate here to say you might also want to identify open problems and anomalies, but really, I think you could get around this. I think you could just have some prompting technique, or once you
Yeah.
have the graph, then you can just ask it to modify the axiom. And actually, explicit identification of open problems could hurt you, but it could also help you. So this is something I would suggest people should explore this empirically. Maybe we'll do that in our paper as well. But then lastly, to spell everything out clearly, you have an idea generation module, which will basically come up with a scientific hypothesis about how to transform the space. So it's a mapping from the space of large language models, L, cross product dependency graphs, cross product open problems, and it maps from there to a space of text and also back to the space of graphs structured according to our definition. So it will come up with text. Imagine an abstract length text specifying its new idea. And then it will also have a new graph that it comes up with.
So I have a quick question on this slide.
Yeah.
How do you encode and decode graphs for LLMs?
One thing that I've been working on is instead of taking the graph and then giving it to the LLM, you take a paper, extract its claims formally, and then list them out. And then you feed those claims to the LLM and let it perform what's called abductive reasoning. So, where it sees a set of evidence or claims and then reasons about like what axioms or higher order rules must have been used to derive those claims. And then you allow it to construct the graph from that knowledge. Once you have the graph, you then retrofit specific papers to the nodes, and then you have a knowledge graph that's been constructed by the LLM rather than one that you originally fed it. Because, I mean, I'm assuming you're skeptic about what happens when you feed a graph with like, I don't know, say 500 papers to an LLM. Like obviously there's a lot of noise there. But this way you get a sort of cleaner construction of a graph without having to filter out uh, like redundancies.
Yeah, we're
Gotcha.
starting.
And
Sorry,
yeah,
go ahead.
sorry. No. Keep going. I have some tangential
Sure.
question. Yeah.
Yeah, we're starting very small. We're not attempting to construct these graphs in their entirety, but more so, um, what we're interested in is the dependency structure. And it's sort of the nice thing about looking at academic papers is and citation networks is by definition they are directed because citation is something that goes through time, and they should also be acyclic because no two papers should be citing each other. Now, sometimes weird things happen with uh, publication schedules, but those are very rare. We're not really encountering any of those. So academic citation networks are already directed and acyclic. And one thing you can do is just go through the citation relationship. Maybe you start with a paper from 2025, an input seed paper, and then you look at what papers that paper cited, and then you apply that procedure recursively to construct a conceptual space. Now, that's easier said than done. So there are a lot of empirical challenges that arise when trying to do this. Um, but hopefully we'll have something into ICLR. And yeah, one thing I mentioned is I'm pretty optimistic about using this framework not just to produce more transformative ideas, but also to enhance interpretability. And as a scientist, if you were to use this idea generation module, then it could be pretty helpful for you because you'd be able to trace the lineage of these ideas, go all the way back to the foundational assumptions that your work is based off of, maybe assumptions that weren't even explicit to you, were just implicitly assumed within it. And then as a scientist, that could help you start to come up with more transformative ideas. Um, I would say the big problem in AI right now, sort of, this doesn't really have to do with the framework here. I'm sort of going on a tangent, but the big problem in AI right now is neurosymbolic approaches. So everyone is keenly aware of the problems with the statistical paradigm language modeling, and it's an inductive system. But earlier attempts to build intelligent systems in the 20th century, like the 1970s and 80s, those expert systems, knowledge based, those were deductive systems.
Yeah.
Those had full verification. You didn't have any distribution. There were no probabilistic guarantees from your training set to your test set. It worked in a purely deductive fashion. And that was great for what it was intended to do, but it was very rigid. Now, today's systems are very loose and they hallucinate, and they're probability distributions in the space of tokens, which it seems to work pretty well for this text generation and these inductive methods. But if you want to do formal reasoning with language models, it doesn't work that well. And you have hallucinations, problems like that. So the big problem right now in AI is figuring out the way to build neurosymbolic architectures at scale, ones that reconcile the strengths and weaknesses of both language models and the earlier expert systems, and builds composite systems that excel at both while doing it at scale.
I, yeah, good point. I think that brings us to the next slide, which is on, or the next part of the, which is on AI Metascience, and I think we can go into discuss this next paper called Active Inference AI Systems for Scientific Discovery. If you're all ready to move on,
Sure. Yeah.
all right,
I have some quick questions for
okay,
Sam.
okay,
Yeah.
So I think you, Sam and Jonah mentioned that right now we are just asking LMs to. I think there's LM plays a role in like constructing the graphs, and I assume it's done in natural language.
Mhm.
So I'm wondering if you see natural language as a bottleneck, especially when your graph gets larger, because I assume the channel capacity is not enough to compared to some other encoding, whereas um, where you can just encode the edges and the nodes directly
Mhm.
into the token space. And I think there was a paper exploring LLM's abilities to understand graphs.
okay,
They tried to encode graphs in different ways to natural language. And I think their
Mhm.
conclusion was it scales up pretty bad. So I'm wondering if you foresee any changes in model architecture. I guess this is more on the implementation level um, to make this work.
I actually had the same thought. One way I can think of to reconcile this is if you have if the LLM constructs a knowledge graph and it gives you two nodes, so one node from which is derived from another node, and you find two papers which represent each node. The walk in the actual citation graph from paper A to paper B can then be added to the graph as like a sort of as context that the LLM missed, but which is substantiated by the literature. So then you have a more fully fleshed out knowledge graph that's consistent with both the LLM's prediction and the actual citation network. But it's
Right, that makes sense. Yeah.
I'm happy to hear feedback on that, though. That was just something that I was thinking about the other day.
I think it's a very interesting point. It certainly speaks to something very fundamental about the limits of language, which is something that is sort of implicit in this entire paradigm that we're going down with language modeling. Um, but again, that would be an axiom, and maybe someone. Well, I think people are exploring foundation models and other modalities. Um, yeah, it's an interesting point. I'll have to think about it some more.
Well, I think that does bring us to the next part too, because which is on active inference AI systems for scientific discovery. And first, I'm going to introduce some more like or first the paper introduces some more kind of specific domain specific systems, and then we move on, and then it moves on to requirements or how a what should be the kind of structure of these more general meta scientific systems. So I just want to briefly talk about kind of the present day advances and like just a few examples of what the present day just to kind of get a bit more concrete about what are the present day advances. So
Sorry, I don't mean to interrupt, but I do have to go. Thanks for having me. Have a good night,
for
guys.
sure, see it.
See ya.
So I think there were so there are a few of these systems that I mentioned, including AlphaFold, ForecastNet, Chembert, uh, SCHNet, Alpha Evolve, Alpha Proof, and Alpha Geometry. And I think these systems, they're specialized systems that can do a scientific task very well. It's kind of like the analogy to chess, where if it's a closed system and it can kind of it can perform very well in this. And they actually used for Alpha Proof, they used Alpha Zero, which is what they use also for chess, the reinforcement learning engine. So, and it won a silver medal in the USA Math Olympiad, which is um, quite impressive. And then AlphaFold has found over 200 million novel protein structures, uh, and then these other ones have done things like sped up the weather forecasting. And then Alpha Evolve also is a really interesting one that DeepMind has also worked on, which is essentially taking a LM ensemble and some evaluation code to generate a bunch of to use evolution. I think it's using combining LLMs with evolutionary methods to find the best program for a given uh, evaluation. And I mean, one thing that I thought of with Alpha Evolve is like, well, what if you're applying that to LMs itself, and then it did actually find a better matrix multiplication algorithm, which is kind of a short step in like in the way of AI improving itself because but I don't think that it was like a 4 by 4 matrix multiplication algorithm, but I think it said they ran AlphaEvolve on like Google's entire code base or something crazy like that, and it found a lot of improvements that it could make. So that's like a pretty impressive application. I think AlphaFold also it's a very specific problem, but it has a huge impact. And these other ones also, so these other ones are also pretty impressive systems, just present day systems. Although they did mention in the paper that um, there are essentially abstraction gaps um, between the different. So like as we were talking about earlier, the scientific knowledge exists on these levels of abstraction, kind of like for example, you could look at a leg or something and say, okay, that's a leg, or you could say, that's a lot of muscle cells, or you could say you could look at the individual cells and say like, what's the I mean, you could look at a bunch of different levels of abstraction of, for example, within biology, but you could also look at the chemical level of the leg or the quantum level. I mean, there are all these abstraction layers of abstraction, but or you could look at it just as a leg, the language level. Or you could look at, I mean, this is just a random example of a leg, but you could really use it. This is how the this is an abstraction gap because um these scientific systems are really used on one level of abstraction, and really what a lot of um what like some people think is that if they're allowed to cross levels, or I mean, they don't really operate on one level of abstraction because they're neural networks, but there are a lot of different layers of abstraction that can change how the that's at least what I understood of the abstraction gap. And then obviously there's the foundation model training efficiency. The transformer architecture is around I mean is an n squared process. So the as the length of tokens increases, it increases in a polynomial. Uh,
Quadratic. Yeah.
what or quadratic? Sorry, quadratic. Um,
Oh, it's technically polynomial, but
what?
there's no there's no attention mechanism that's more complex than quadratic for now. But it's technically polynomial. But still, keep
Okay.
going. Never mind.
Okay. Yeah. Well, either way, the attention mechanism is. I'm not saying it's because it's done so many amazing things. I'm not saying it's inefficient, but for certain tasks, especially long sequence tasks and tasks operating not on like a language level, there might be different models that are um, more efficient. For example, uh, I know that some of the state space models are tending to perform better on certain sequence tasks, um, in terms of inference and in terms of the length of the sequence, because of um, they're not actually n squared. So, but the transformer, well, that is a problem with it. That's also a feature because it's comparing every token to every token really in some way. So it's like it's a kind of a feature and a bug in some way of the, but it just limits what can be done with the transformers. So um, I don't think that all these models are using transformers, but especially the Alpha Zero, which is mostly a reinforcement learning um, system. So, but that brings us to the next point, which is like, which kind of are what would a future system need in order to um, perform complex scientific discovery that isn't relegated to this specific domain. And it, I mean, and their principles of active inference, and I think active inference is this um, type of type of inference stemming from the free energy principle, in which systems minimize their prediction error in both the uh, environment, like they take actions to minimize prediction error, and they also change their model to minimize prediction error. So I'll just read this quote from Carl Friston, or Friston. An active inference behavior has explorative, epistemic, and exploitative pragmatic aspects that are sensitive to ambiguity and risks respectively. Where epistemic ambiguity resolving behavior enables pragmatic reward seeking behavior, subsequent emergence of habits. So, and then the from the paper.
Yeah, so sorry to interject. I would just say this exploration exploitation trade off certainly seems to be this fundamental pattern in all of intelligence. And you can look at this at a very mathematical level in terms of reinforcement learning. There's a lot of research that goes into what are optimal schedules for exploration initially and then exploitation once you think you have a good enough behavioral policy. So this is something that I've been thinking about a lot: exploration versus exploitation. Um, and even on a phylogenetic scale, if you look at human evolution, it seems that there's a lot of that going on as well. Exploration in DNA space. Um, Maybe the exploitation isn't as clear, but you can look at that in terms of natural selection.
Yeah, I mean, I think it's even shown on like a neuroscientific level. I've been reading this book, Principles of Neural Design,
Mhm.
and essentially it's talking about how it's just a common like element of the brain is trying to estimate whether it should go explore a different area, or like in the most simple biological systems, like even the C. elegans worm, like whether like there are aspects of the brain that depict whether it should like all these things, these aspects are like whether it rests or whether it explores, or you know based on the amount of food, based on the amount of resources. There are all these things that in these very small brains or whatever, they're still thinking about. It's like, so it is a pretty fundamental principle, I think, of biological systems, and just
Yeah, so suppose you could build an active inference system from really from scratch, and scale its architecture to the point that today's architectures like GPT and Anthropic, their models. My question would be, would these deductive logical, as the author of this paper points out, would these discrete logical structures emerge from that active inference system, similar to how they've emerged in humans on a biological level? Or do we actually need to explicitly engineer knowledge graphs, uh, deductive reasoning? The question fundamentally boils down to, can you actually build a general architecture through which deductive and logical reasoning would emerge, and staying consistent with the bitter lesson? Because you might, are you familiar with the bitter lesson from Rich Sutton, by the way?
I am not.
Okay, it's very short. I would definitely suggest reading it. But his basic claim is that the general trend that he's observed in the past 70 years of AI researcher, this guy Rich Sutton, he's been around for a while. He's like the father of reinforcement learning. But the general trend that he's observed from 70 years in research is that general methods which leverage learning and search tend to outperform specific designed methods, say feature engineering from human scientists. The better long term solution has always been just think one level of abstraction higher and then scale the computation around that more abstract architecture. And as long as you scale learning, scale compute, scale data, then those methods tend to outperform. And this has been corroborated by the scaling laws, right? The chinchilla scaling laws. So my question is, say you can build a very general active inference system, will these discrete logical structures and the ability to manipulate them properly as humans do, will they actually emerge in such a system? It's a very open-ended question. Obviously, there hasn't been breakthrough progress in that area, but I just question whether, as this author of the paper here has outlined, in order to do reasoning, you need knowledge graph architectures, traversal policies, neurosymbolic stacks. But my question is there something that's actually one level deeper, where if you can just figure out what that is, maybe it's active inference, maybe it's something else, but some general principle, a general framework around which intelligence emerges. Can you scale computation and data around that? And can all of these human-like abilities emerge as a result of that. Now, that's an open question. No one has an answer to that, but that's something that I certainly think about from time to time.
Any thoughts? Other thoughts about this question?
I think that's a really good point. I was going to ask Sam and I guess everyone um, whether kind of encoding the theory of creativity or like forcing a specific pattern of creativity through either graphs or whatever architectures would run contrary to, I guess, the bitter lesson. But I guess we're at a point where data isn't getting any more. Like all of the big companies have scoured the entire internet. They're looking into vision, but the the information density is quite a bit lower. So maybe it's time to consider if you can scale data and compute to the next order of magnitude, maybe it's time to consider kind of encoding some kind of structure of knowledge into the model itself instead of just scaling as we did over the
Yeah.
last decade.
Yeah, right. The general pattern is you need abstraction, you need representations, you need to compose representations to make those abstractions, but the attention mechanism is not set in stone. The current neural network architectures are not set in stone. So maybe the next 50, 100 years, those could look a lot different. But I would argue as staying consistent with the almost 300-year-old tradition, and maybe it's even older than that. But starting with Kant, Critique of Pure Reason, the system of knowledge and being, you certainly need representations and you certainly need to compose them. But the type of architecture, maybe it's not a transformer, maybe it's something else.
So going back to
Right.
the
I don't think
like alpha evolve thing, I think it's or the alpha evolve architecture. I think it's interesting like that they're kind of like how they're using evolutionary algorithms to um a, a, evolutionary algorithms on top of LLMs essentially to find better programs. This just came out in
Mhm.
2025, I think. Like
Yeah,
this
it's a new paper. Yeah.
um and I think this is kind of a I mean I'm not saying this is the solution or whatever. I'm obviously but it's just like an interesting it brings me back to this point of how you were saying that like the bitter lesson where the more general systems or more even the ones that are um, on a different level of abstraction or in just a higher level of abstraction. I think this alpha evolve is kind of something that we can look at, something that I at least will look at and say like um, and think about how it's really focused on this layer of abstraction uh, that it is using LLMs, but it's also using other algorithms too. I think it's kind of a meta it's a meta use of LLMs in some way because it's not just because it's not reliant on any one on the training of an LLM. It's using the evolutionary algorithm to pick what the LLM's output. And I think there was also one where like an LLM tried to improve itself um using an evolutionary algorithm. It would like try to it would create successive versions of itself and then um it like each output would be the code and then it would have some goal as well. But I think a problem with that is how do we actually maintain a memory of the initial values of a system such that it won't explode or won't decay um through time of the initial values of a system. Like if it's self-improving. Um, and I don't know exactly how to create a self-improving. I mean, self. I mean, that's kind of the the question is like, is it going to be AI that improves itself? Like AI has to improve itself, right? So, because or if AI, that's when the kind of in philosophy of artificial intelligence, that's when the singularity would emerge, or the intelligence explosion would emerge, is when AI can improve itself faster than humans can. And I think this evolutionary approach, like the LLM, like what if someone applied elf evolve to itself, or I mean, how would its values kind of align with humans? That's another. I mean, that's not necessarily the question of science, but how would it even? But I guess the process, the problem of memory within these self-improving systems is also kind of a question. I don't know if these self-improving systems actually. I don't think I haven't seen them at least as explicitly as just they are like like humans using LLMs to program more to like create new architectures or things like this. That's like a kind of an implicit loop, but there I haven't seen the explicit loop yet. But I think this is one step towards that. So, uh, do y'all? I mean, do you think that it has to be self-improving, or like or do you think that fundamentally there's not enough data for it to do that, or does it have? Do we have
I
to?
think
Go ahead.
I think just to jump in, sorry. I think it could be just like a mix of both, honestly. But I mean, to your point about like valid, like the whether a self-improving model will be able to improve, like remember its original values. I think because it's self-improving, those values might change. I don't know. I think that concept is pretty nascent for me, but I think like I think we'll definitely have to see. It also could be probably a data thing. And something with the model foundational in itself. But to that point, I guess I'm curious. I would love to hear your guys' input. Going on a tangent here, sorry, but um, in self-improving model, like self-improving models, those values, those original values, would they change? And if they change, how would be able to keep up? And maybe does that lead into the concept of singularity in the future?
Yeah, I mean, I think it is
Does that make
a.
sense?
Oh, go ahead.
Yeah, sorry, no. Does that make sense? Might might be confusing myself here.
Yeah, I mean, I think the um that is a fundamental problem with the intelligence explosion type idea, is that the um the value, the human, the like the capacity, like if it's self-improving, then what, then like how does it maintain some sort of base value system even as it changes across different architectures? Um, I think the the value system, like I think there's a, like in this example they have an agentic layer, or the value human specification, and they have humans in the loop. Um, I think that's one way. I mean, if we just look at the current LLM and reinforcement learning with human feedback, they rank order responses based on what humans chose. Um, I don't, but I think as these models become self-improving, they're going to need to remember how the initial values that it had. Like if you can align one model and then you can have it say modify its own code to um, then like yeah, I guess it's a question that I think is really open, but I think it has to have some sort of control layer and has to wait. It has to remember the previous models. I'm not. I still have to think more about how exactly that is. I mean, it's one of the probably like how do you like, because these models have not been really created yet. There's only kind of they're theoretical, like Gödel machines, and in this kind of like one example is this alpha evolve. It's one of the most recent examples, and I think yeah, it's going to be a question in the, like how do we encode our values in the self-improving system such that they maintain their weight in the future. But yeah, going back to the scientific points, so do you think that this I guess we could just look at this like this setup they have here. Do you think that this suffers from the problem that you were talking about earlier, Sam? Like, do you think this is like that this is too specific of a specification?
Yeah, in the long term, it probably is. That's not to say it's not correct. Uh, I mean, we know that these these architectures are very helpful for humans, but in the long run, maybe explicitly engineering AI systems around them could be detrimental.
I do think to scale beyond human intelligence, eventually we'll need something like what Sam described, a generalizable abstraction where the model could map uh, different things, create those mappings themselves, and perform deductive or whatever kind of reasoning on those structures. Because I do think today's RL landscape is a bit misguided, especially with reasoning. Because if you look at recent attempts um, in improving reasoning models, well, I guess we started from COT, and then we found we didn't have enough data, so we have RL with verifiable rewards now. We generate some grade school problems, maybe not grade school, high school math problems from a graph, convert that to natural language, and then trained the model on that and found, oh, the model's reasoning capabilities generalized beyond high school math problems. Uh, but it does feel that we are kind of missing the mark on allowing the models to create some kind of rewards incentive structure themselves, because even if, like, suppose we knew exactly how to train a human mind, like suppose we like completely understand the human mind, we completely understand the theory of creativity, we can perfectly replicate that. Even then, um, if we encode that into model architecture, it's still like the most it could do is the specific tasks humans are good at. So I do think it's an interesting question of how to allow the models to scale beyond that.
Yeah. So what I will say is the I don't know if everyone was here when I said this, but another one of the papers we want to get into ICLR is this fall is theory for the emergence of creativity in language models. So this is one where we're basically going to introduce mathematical constructs at a very mechanistic level that relate to the creative abilities of language models, but really any sort of large scale connectionist architecture. And it sort of boils down to a lot of concepts that have been thrown around in cognitive science for a while. Um, you can think of the connectivity of someone's brain. There's this paper from 1962, which introduces this notion of an association hierarchy. And essentially, it's asking or probing. Imagine you have a brain and it has concepts that are all connected together in this large graph, and you can have multiple edges between concepts. One view is that more creative people, and I think this has been substantiated by literature and psychology, more creative people have more connected brains in terms of concepts. So if I were to say the word table, then the concepts that they would evoke in association to that would be more uniform. So they would have more connections between the word table, say to the word chair, cloth, wood, leg, food. Whereas someone that is less creative might only think of one or two things that are related to table. So that's that construct of degree of connectivity is one which I think is very helpful. And what we want to do is understand to what extent language models are really connected in this way. And at some point, I would think this construct can lead us to develop architectures which are more connected in this sense and could lead to more creativity. I can only speak to creativity, that component of intelligence, but the other areas, deductive, causal, logical, mathematical reasoning, it would be helpful to develop these more general accounts and more general probes into the abilities of today's architectures, see where they're at, and then from there, see if we can build better architectures um, around which computation can be scaled. But I do have to drop off.
All
Thanks
right.
for organizing this. This was great.
All right.
And if anyone has any questions about the work, obviously feel free to shoot me an email. Happy to discuss or anything that we talked about today. If you want to follow up on that, I guess I'm in the Discord as well, so you can just message me on here too.
Awesome. Thank you. Thank you, Sam. Uh, thanks everyone for coming.